Gavin Jones, and through an experiment of my own setup, I chose to analyze the potential of 2 aquatic plants in filtering 2 abundant chemicals from human urine. To begin, it is important to address the fact that the human race is accelerating rapidly towards life beyond Earth. One crucial component to life as we know it, no matter how far we are from this world, is water. Several methods exist now for water in space. One method is, of course, to send water directly into space. This is very expensive, however, considering the weight of water and the fuel that must be used to get a rocket into space. Another method is called the water recovery system. With this, water from urine, sweat, and other human excretions can be extracted. One component of this is the brine processing assembly, which is specifically used for urine filtering. Yet another process, an enhanced version of the Sabatier process, forms water from hydrogen and carbon dioxide. Even with these methods, however, it is known that an astronaut must limit their water usage to a fraction of what an earthbound human can. For instance, the average person here on Earth uses about 80 gallons of water a day. An astronaut must use 1. Very efficient and less expensive methods are certainly not yet in our grasp. Now, before I decided to analyze plants as a filtering method, I first did a review of the related literature to determine what method would be most feasible for use in space. The criterion involved in this would be that the method be independent of gravity to function. One important source I found was the research done by Catherine Borer and her research team. In this study, the researchers studied the effectiveness of X-packs. With these, salt pulls water through a semi-permeable membrane through a passive process known as forward osmosis. Their intent was not to use the treated water for drinking. Rather, it was to make disposing of urine on caving expeditions more environmentally friendly. The researchers found X-packs suitable for this purpose. However, only 67% of urea, a chemical abundant in human urine and not suitable for human consumption, was removed from the water. Thus, X-packs are not suitable for filtering urine into drinkable water. Another important source I found was the research on constructive wetlands by Christopher Ackenbile and his research team. These researchers studied the use of plants to clean water, a process known as phytoremediation. To do this, the researchers used a constructive wetland, or an artificial flooded area. This image depicts such a constructive wetland, where here we can see the plants, and below that we can see the constructive wetlands itself. The researchers built the wetland to test a plant with potential phytoremediation capabilities, known as Azolla pinnata. The researchers found that Azolla pinnata worked well in removing many chemicals from the water. The use of plants for cleaning water stood out as a potential method for my research because plants are 1, cheap, 2, can be reused in filtering urine, and 3, can be used as a food and oxygen source if need be. Constructive wetlands, however, are dependent on gravity to function, as you can see in this image, and thus are not suitable for use in my research. A third source expands on the aforementioned method of phytoremediation by studying a plant that grows independent of gravity, the submerged water plant Nelumbo nucifera. In this study, Esthamtha and their research team tested Nelumbo nucifera in its removal of phosphorus from contaminated water. Although they found high phosphorus removal efficiencies from the water, it was mostly due to the soil. Though the plant was deemed too difficult to acquire for my research, and despite the fact that they only tested for phosphorus removal, this shows that methods for filtering urine that are independent of gravity do exist and do show promise. The research done by Paride Papadia and their research team reveals a plant with potential for use in my research. These researchers studied Taxiphyllum barbarei, more commonly known as Java moss, and its removal of heavy metals from contaminated water. Their results showed that Java moss works well at removing heavy metals from water, which reveals a plant with potential for removing chemicals from urine. Furthermore, this plant has little literature on its phytoremediation capabilities. My review of the related literature eventually led me to choose 2 plants, each of which have little to no research on their phytoremediation capabilities, thus demonstrating a gap in the body of knowledge. This led me to my research question. What are the capabilities of Lysimachia nummularia, or golden creeping jenny, and Taxiphyllum barbarei, or Java moss, in filtering urine into drinkable water? Given that there is such a large variety of chemicals in human urine, I decided to test this with only 2 chemicals, urea and potassium chloride. These 2 chemicals are abundant in the average person's urine, and the results of this study would provide future researchers with information on whether or not these plants should be studied further. My experiment originally consisted of 16 Java moss and 80 golden creeping jenny plants, which were all obtained from a local fish store. I determined the mass of every Java moss plant and the length of every creeping jenny plant prior to the experiment. The Java moss was placed in glass containers, and the creeping jenny plants were planted in buckets during the course of the experiment. All plants were submerged in distilled water. The glass and buckets were all sterilized, and the plants were placed randomly and evenly. Loose plastic wrap was draped over the tops of the containers and buckets to minimize water loss due to evaporation. Because Java moss grows best with indirect light, I also loosely placed aluminum foil over the tops of the Java moss containers. Now, it is important to note that the initial plan was to test 3 chemicals. Thus, the plants were set up in 4 groups, 1 control and 3 treatments. As time wore on, I determined that I would not be able to test for the concentrations of 1 chemical, and the experiment changed to only 2 chemicals. This occurred after adding the chemicals to the groups, however, so the plants could not be rearranged, and the total number of Java moss and creeping jenny changed from 16 and 80 to 12 and 60, respectively. Following the setup of my plants, the chemicals were added. As I mentioned previously, urea and potassium chloride were chosen due to their abundance in human urine. Before I explain farther, it is crucial to recall that the purpose of this experiment is not to test for the exact and specific chemical concentrations of urine. Rather, it is simply to test 2 abundant chemicals that are found in urine. Thus, I did not use the same concentrations of these chemicals that are in urine for my experiment. For the Java moss treatment groups, I used 1 gram of urea and 0.75 grams of potassium chloride. For the creeping jenny groups, I used 10 grams of urea and 8 grams of potassium chloride. These images show the final setup of the experiment. In this image, you see no plastic wrap, and that is solely for the purpose of the image. The experiment lasted for a total of 42 days following the addition of the chemicals, which included 21 for acclimation and another 21 for sampling. Beginning on the 21st day, a total of 3 potassium chloride and 4 urea tests for the creeping jenny control and treatment groups were taken. The Java moss groups were only tested once at the end of the experiment. The samples of each creeping jenny group were analyzed weekly. Samples were brought to Missouri Western State University to use their spectrophotometers. To establish a baseline for every test, control groups of each plant were tested along with their respective treatment groups. Urea samples were analyzed using a modified Watt and Crisp method, which essentially involves a reaction with hydrochloric acid that makes the solutions visible to the spectrophotometer, the reaction of which is shown here. Now, prior to mixing the hydrochloric acid, both the acid and the solution, the standard, were clear. And as you can see here, this reaction resulted in a yellow-tinted solution. The potassium chloride concentrations were determined by analyzing the potassium ion content. For both urea and potassium ions, the spectrophotometers do not directly measure concentration. Instead, they measure the absorbance of a certain wavelength of light. This absorbance was determined with pre-made standards of known concentrations, creating a scatterplot of measured absorbances against known concentrations for every test. These scatterplots would then be fit to a regression line, the equation of which, along with the measured absorbances of my samples, would be used to determine the unknown concentrations of my samples. An example of such a scatterplot is shown here, where on the x-axis we have concentration, the y-axis we have the measured absorbance, and each plotted point here is the measured absorbance for known concentrations of my standards, which was then, as I said, used to fit the regression line, the equation of which is shown up here. Now these also have an R-squared value. This is called the coefficient of determination, and its proximity to 1 determines how linear, it shows how linear the data is. As you can see here, this R-squared value is very close to 1, meaning that the data is very linear and can be used to reliably calculate the concentrations of my samples. The R-squared values for all of my scatterplots were close to 1. Now, as I previously mentioned, I calculated the concentrations of my samples using the equation line for the regression line, for the regression line for each session. These concentrations were given as either grams or milligrams per liter, so I had to do some more quick calculations to determine the actual concentrations of potassium ions and urea in my groups for each plant. These tables show the actual concentrations for every group. It is important to recall these potassium measurements are only of potassium ion content, not of the potassium chloride. Since about half of potassium chloride is potassium ions, these numbers could be doubled to get the actual potassium chloride amounts. Instead of doing this, however, I took my initial potassium chloride concentrations and divided them by 2, resulting in approximately 4 grams of potassium ions for the creeping jenny and 0.38 grams of potassium ions for the Java moss treatment groups initially. Thus, the figures shown here for potassium concentrations should be compared to the initial potassium ion concentrations that I just gave, not to the initial potassium chloride concentrations. As for urea, recall that I used an initial concentration of 10 grams for the creeping jenny and 1 gram for the Java moss. Now, before I explain the data itself, you may have noticed that when we look at the creeping jenny results, many of the measured concentrations for both potassium ions and urea are higher than my initial concentrations. This is intriguing, and although I was unable to determine the reason for this, one might suggest that interference could play a role, that the creeping jenny plants could have released some substances into the water, or that the lighting in the room at the time of measurements could have some effect on it. However, if you look at the measurements for the control groups, you will see that they were always very close to 0. Therefore, it could be decided that interference did not play a role in these unexpectedly high values. Furthermore, considering the purpose of this research, I decided that the reason for this is not necessary. Remember, the purpose of my research is not to test the exact efficiencies of the plants, but rather to determine if these plants should be studied farther. Thus, only the trends of the data are important. By looking only at trends, you can see that the initial potassium ion concentrations here for creeping Jenny stayed pretty much the same throughout the experiment, and thus so did the potassium chloride concentrations. On the other hand, its urea concentrations went down by about 2 grams each week. This shows promise for the first 2 weeks, or first 3 testing sessions, although there appears to be no difference between the concentrations at the 16th and the 23rd. As a result of all of this, I cannot conclude that the golden creeping Jenny plant be studied farther in future applications regarding urine, filtering urine, rather, despite the fact that the urea concentrations decreased steadily over the first 2 weeks of testing. For the Java moss, recall that the initial concentrations were 0.75 grams of potassium chloride, or approximately 0.39 grams of potassium ions, and 1 gram of urea. You can see in these tables that the concentrations for both urea and potassium chloride decreased by a large margin. Again, this does not mean I can conclude that the plant is necessarily efficient in removing these chemicals from water. Instead, I can conclude that Java moss shows potential and should be studied further in future applications.